will have problems with each component. Resistive and NTC, or negative temperature coefficient. This is a product of Advanced Digital Hardware Design course by Philip Salmoni. You will see its course here at Fideville Academy, Controlling the Slow Rate. Hi everyone, how are you doing? I'm Abdelhamid Hilal, and in this episode we're gonna speak about Inrush current control. As you can see over here, we have spoken about how smart your power switch must be in the first episode on LinkedIn. I'll put its link in the video description. So first, what is the problem with Inrush current? As you can see over here, this figure, we have power supply, switch and load. So the Inrush current will have problems with each component. First, the load, switch and power supply. Let's speak about the problems with the load, especially if you have a heavy capacitor at the load. This will withdraw high amount of current, which is called Inrush current, and this may cause a failure to the load, or at least shorten its lifespan. And this is also happening to your power switch. This power switch typically be a MOSFET. So if the Inrush current is higher than the maximum current the MOSFET can handle, so the MOSFET will be burned out, or at least you will shorten its lifespan, especially you don't have a snubber circuit about its terminals. Let's speak about the third problem with the power supply. When you withdraw a high amount of current, this will result in a high dip in voltage of your power supply. So what is the problem of this dip in voltage? The problem is that if you have another system is powered from this power supply. Let's make an example. As you can see over here, this figure, we have input supply and we have a switch to a system and DC-DC converter to another system. So if this heavy capacitor withdraw high amount of current, we have said that a dip in voltage will happen at the input supply. So the problem is that the DC-DC converter will restart. So the problem is that if you have a system, especially a microcontroller or FPGA powered by this DC-DC converter, you will lose all the data you have in this microcontroller or FPGA. As you know, FPGA, if you have restarted or if you shut down the FPGA, you will lose the configuration file and you will have to re-upload the configuration file to your FPGA. So this is a problem of dip in voltage. So we have three problems of Inrush current: problem of the load, problem related to the switch, and third problem related to the power supply. And what are the solutions of this effect? We have two solutions: passive and slow rate control. Let's speak about first solution, which is called passive solution. In this solution, we have two sub-solutions: resistive and NTC, or negative temperature coefficient. Let's speak about resistive. You will put a series resistance. So what's gonna happen? The Inrush current, or the total current of the circuit, will be low by the addition of this resistance. So the current will be Vn over R. You will calculate your current withdrawn in this circuit. The advantage of this solution, it's low cost and easy to implement. By the disadvantage of this solution will be the power dissipated in the resistance. Another sub-solution of the passive solution will be NTC, or negative temperature coefficient. As you know, this NTC is a resistance dependent on the temperature. So when the temperature rises, the resistance will decrease. So at the start, the NTC is cool, so that the resistance will be at its maximum, so the Inrush current will be low. After a short amount of time, so the power dissipation will make the NTC heat up, and this is an NTC. When the temperature rises, the resistance will be decreased, so the resistance will be decreased and the load or your system will be fully on or will withdraw its full rated current. The advantage of this sub-solution is low cost, easy to implement, and also it is less power dissipated than the resistive. But the big disadvantage of this solution, if you shut down your system, so your NTC will still hold and its resistance will still low. You will wait for that. The NTC will get cold so that you can turn on or you can power up your system again. The second solution is controlling the slow rate of the MOSFET. You will control the switching speed or the time of turn on your MOSFET. It's like an opening a room door. When you open your room door, you will turn on or you will open it slowly. So that is the concept of controlling your MOSFET. You will turn on the MOSFET slowly. So this is the input voltage, the hard transition of input voltage. When you control the turn on time of your MOSFET, you will get this curve of V out, smooth transition, and this is the target we're gonna make. You can control the turn on time of your MOSFET by an RC as you can see over here in this figure. I don't prefer this solution because all the components are discrete. Your power MOSFET, drive MOSFET, resistance, capacitance, all the components are discrete so that they are not accurate 100%. So I prefer making all the components in a package which you will see in E-fuse or load switch or something like that. As you can see over here, I am working on project of Z-Bret or Z-Board. This is a product of Advanced Digital Hardware Design course by Philip Salmoni. You will see its course here at Fedeville Academy. So this is an input plug, a barrel jack, DC barrel jack. We have here 5 volt, and we have here an E-fuse. The E-fuse itself has a built-in MOSFET. So we're gonna control the turn on time of this built-in MOSFET by this pin, SS, soft start pin. It depends about the amount of capacitance you will connect to this pin, so you will control the turn on time or rise time. As you can see over here at this table, if you put 100 nanofarad, so the rise time of your MOSFET will be 25 milliseconds. And if you don't have any capacitance of this pin, you will have a programmed or default rise time which is 1.7 milliseconds. As you can see over here, the datasheet of this E-fuse, we have this option 5 volt mode and CSS is 100 nanofarad. So this is the hard transition of your voltage V in, and this is the soft transition of V out.